Hello everyone and welcome to this week's Seds Online webinar. We're really pleased to be able to offer all of our events to you for free thanks to generous sponsorship from the International Association of Sedimentologists, the IAS. This week we're really pleased to be able to welcome Gino, Massimiliano Ghinassi, who completed his master's degree in geology at Florence University in the year 2000 before going on to complete his PhD in 2004. Gino did his PhD at Siena University in sedimentology, specifically in basin analysis of a Pliocene basin in the northern Apennines. He then went on to do a postdoc from 2004 to 2007 on the Pleistocene to Holocene deposits in East Africa. In 2007, he began his role at the University of Padovav in Italy in the Department of Geosciences, where he is now an associate professor. Gino has over 100 publications and over 1,000 citations specializes in the field of fluvial sedimentology, and he's going to be talking to us today about some of his research in this area, the ugly duckling of coastal environments. So without further ado, I'll hand over to you, Gino.
Hey, thank you, Catherine, for this introduction. Welcome, everybody, and I hope you're ready to listen some tales about ugly ducklings, okay? And actually, I have to point out that this term, the ugly ducklings of sedimentology, was used for the first time by Wojciech Nemec. A nice idea, nice term to describe colluvial deposits, which were commonly widely misregarded by many researchers over the years until he published around the end of the 90s nice papers about sedimentary facies of the deposits, revealing that they can be an outstanding archive in terms of information for sedimentary processes, especially for those associated with the gravity-driven flows. And we have actually several examples about ugly ducklings in sedimentology. Just think about travertines and calcareous tufa. And if you think about the number of publications about these deposits across the discovery of the pre-salt reservoirs offshore of Brazil, we clearly see that across this discovery, the number of publications about these deposits increased significantly, three times more in 2014 compared with 2004. And this increase in interest revealed that these deposits are a precise archive, not only in terms of property of rocks and other things tightly related with oil exploration and reservoir development, but in terms of many other informations. Today, I'm trying to tell you something about another ugly duckling of sedimentology, of coastal sedimentology. I will focus on microtidal meanders, and I especially discuss morphological and sedimentary features of microtidal meanders developed in the Venice Lagoon in Italy. Actually, before to talk about ugly ducklings, we should immediately point out something about the swans. Actually, we know that if we look in textbooks about something about sedimentary facies for tidal pointwars, the tidal meandering channels, all the textbooks are pointing out to the best examples. And we know that most of the facies models for tidal meandering channels and related deposits are actually developed in the Bay of Fundy. Recently, a lot of papers by Kyung-Sin Choi and from the west coast of Korea, or other studies from the Mont Saint-Michel Bay. Actually, in this setting, the swans are really demonstrating, are really showing that within tidal point bars, tidal signature can be very clear, and tidal cycles are pretty well recorded at different scales. Nevertheless, if we consider the distribution of the tidal range all around the world, we can clearly realize that macrotidal to hypertidal settings are not so widespread as microtidal ranges. And in a sense, this would be like develop fluvial facies models only for large-scale rivers, okay? But we know that small rivers are quite widespread all around the planet. So actually, today I'm trying to shed some light in deposits developed in a macrotidal environment. Macrotidal systems commonly are quite disregarded because we know that tidal signature in these systems is commonly not preserved, simply because other processes can overwhelm tidal processes. In macrotidal systems, tidal processes are commonly overwhelmed by wave currents or fluvial currents. But if we think carefully about where we can find sedimentary products of microtidal systems, we can realize that actually microtidal channel networks are a perfect place to study the sedimentary products of tidal currents developed by a microtidal range for two simple reasons. Actually, in these channels, there is not enough fetch to develop wind waves, so tidal deposits cannot be reworked. And also, if we consider purely tidal channels, for sure, we don't have any connection with the fluvial discharge. So this is, in a sense, the perfect place if we want to try to understand what is the tidal signature in a microtidal system. Actually, these deposits, these channels are not so uncommon. Just think about the Gulf of Mexico, where just keep the Mississippi Delta, obviously. And in this setting, we can find very complex network of these tidal meandering channels, and they can propagate from the coastline several kilometers inland. So they are quite common, they are quite well developed. They also occur in obviously in the Mediterranean Basin, and where the Venice Lagoon here in the northern portion of the Adriatic Sea is sited. And the Venice Lagoon, as you know, is the goal. The microtidal channels of the Venice Lagoon are actually the goal of this talk. Just before introducing some features about the lagoon, I need to acknowledge the research team I'm part of. My colleague and friend Andrea Dal Paus, he introduced me to the Venice Lagoon morphology and sedimentary process just few years ago, and the other guys, which are now belonging to the group, postdoc and PhD students, Alvise Finotello, Marta Cosma, and Elena Bellizia, and all the other friends and colleagues who contributed to most of the concepts I'm going to show you in this presentation. So, a few words about the Venice Lagoon, just to understand where we are and the overall geological and geographic setting. The Venice Lagoon was generated during the Holocene transgression. It has a barrier that isolated the lagoon from the sea, three main inlets, Lido, Malamocco, and Chioggia. Actually, the Venice Lagoon is the largest brackish water body of the whole Mediterranean area, almost 500 kilometers square. In green here, you can see the present-day salt marshes, almost unluckily just 40 kilometers square, and unluckily the surface, submerged surface, is quickly decreasing in the lagoon. They have an accretion rate that over the past century ranged between 0.1 centimeter to 1.4 centimeter. And the water depth in the lagoon is quite shallow. Subtidal platforms are just slightly more than 1 meter deep. Channels close to the inlets can be up to 15 meters. The tidal range, tidal regime, is just plus minus 70 centimeters around the mean sea level, and the exceptional tides can rise up to 2 meters. Actually, the grain size within the lagoon is on tidal flats. We are dealing obviously with mud, and channels, they mainly transport the silt and sand. And we will see later some details about the grain size within the channels. And actually, the lagoon does not receive any fluvial input at the present. There are just two main rivers which are entering the lagoon in the northern part, the river and the rivers. These are spring rivers. They are small, they have a quite limited catchment that is developed in the coastal plain. So actually their contribute in terms of sediment load is almost null. How do we move sediment within the lagoon? Actually, the wind play a key role in the mobilization of the sediments. We have two main winds which are blowing on the lagoon. The Bora wind, which comes from northeast. This is a strong wind, and actually, because this wind almost blows along the axis of the lagoon, there's a quite good fetch because the lagoon is almost 15 kilometers long. And in this case, during the Bora events, we can develop quite big waves to be in a lagoon. They can move the bottom up to also in 1.5 meters deep water. So all the tidal flats are stressed, let's say, during these Bora events. And actually during these events, most of the mud is suspended, but even during the stronger events, the maximum concentration for this sediment is slightly more than 200 milligrams per liter. So I can clearly state since now that we are quite far from conditions allowing formation of fluid mud. The other important wind for the Venice Lagoon is the Scirocco wind, which is coming from the south and causes a quite important coastal setup within the Adriatic Sea. And in this case, of course, the Scirocco wind can amplify the astronomical tides. So let's say that the Bora wind is important for waves and the Scirocco wind is important for tides. In the lagoon, we have a quite complex network of tidal channels. Most of them are draining salt marshes. Some of them are draining subtidal platforms. So we are dealing also with subtidal meandering channels. In this framework, I will try to focus on these main points. I will discuss insights about the planform morphology and migration rates of these channels, possible planform transformations and flow patterns within these channels, the relationship within lateral migration of channels and vertical gradation of the overbank areas and their effects on point bar deposition. Then we will deal about bar deposits and the tidal signature on these deposits. And then I would like to focus on the morphodynamic evolution of some subtidal meanders, which has been commonly poorly described in literature. So let's have a look at the planform morphology and migration rates of these tidal channels. Actually, most of this work has been carried out by Alvise Finotello, and Alvise characterized morphology of large number of channels within the lagoon, following the approach proposed by Marani in 2002. And he measured essentially different wavelength within the single meander bands, the intrinsic wavelength, that is the length along the channel, then the Cartesian wavelength is simply the distance between two adjacent inflection points, and then the landward and seaward length of the meanders, the single meander, defining in this way different parameters which allow to characterize morphology of these bands. Of course, the radius of curvature was also considered. Just because before looking at the morphological characterization of the bands, another feature he considered was the aspect ratio of these channels. Here we have some results from measurements concerning the width to depth ratio of these channels. In red are the channels from the Venice Lagoon, and in blue we have other data from US East Coast, from channels developed in a mesotidal range. We can clearly see that they almost, actually they almost overlap. This means that the tidal range doesn't have any significant role in shape the geometry of these channels. And actually we can also see that fluvial channels has almost the same width to depth ratio. So in terms of geometry of single channels, we can move from low to high tidal range, and the width to depth ratio seems to be quite similar. Actually, we got similar results considering also the planform morphology of these channels. Actually, here you have in blue the dataset from the Venice Lagoon, and other colors, and the gray color are about tidal channels from different sites in the world, sampled from different tidal ranges spanning from meso to macrotidal, and you can clearly see that the ratio between considered parameters, for example, width and Cartesian wave length or the band amplitude, they clearly overlaps. So actually, the tidal range doesn't play any key role in shaping this channel. So, and the channels, the microtidal channels of the Venice Lagoon, the meanders of the Venice Lagoon, are in terms of shape quite comparable with other bands formed in different tidal ranges. Actually, we analyzed also migration rate of these meanders because they were considered by many authors quite lazy channels in terms of migration rate, and considering the relationship between the migration rate established by observing the shift of the center line across time using aerial photos of different ages, and actually plotting the migration rate with the radius of curvature, in both cases normalized by the width, that is actually the size of channels, we got something like this diagram. And if we consider fluvial meanders, which are commonly considered much more active from published datasets, we can clearly see that actually the migration rates of the lazy tidal meanders of the Venice Lagoon is fully comparable with that of fluvial meanders if the migration rate is properly normalized with the local channel width. So actually, these channels are not so lazy as many people said. Simply, these channels are small and they move slowly. Actually, we can also look at the planform transformations of these bands. Actually, comparing different aerial photos from different years, we managed to identify, this is a qualitative approach, different planform transformations. Actually, we define four main transformations following the terminology that is commonly used in fluvial channels. We identified tidal channels characterized by an expansional behavior, translational behaviors, straightening to spate, and stable. These are the new terms we used. Actually, we pretty well know what is expansion and what is translation. In case of expansion, a band is classically increasing its own sinuosity, and this process commonly culminates in the meander band neck cutoff. In case of translation, the sinuosity is kept almost constant, but the band is translating, in case of rivers, it's commonly translating seaward, downstream. In this case, we have a translation of a seaward translation of the tidal band with erosion on a side of the inner bank and the position the other one. Straightening to spate is a quite unusual behavior, because actually if you compare the planform in 1968 with the planform at the present day, we can clearly see that these two bands, they decrease in sinuosity, actually storing sediment along the outer bank. This is very unusual. And then we have a stable to spate form, which actually represents a very stable form. Actually, no changes for this small band since 1955 to the present day. Actually, we recovered several cores from this for the point parts associated with these bands, and we carried out some ADCP measurements, which were actually carried out at the maximum flood and ebb velocities. So let's have a look of the data we recovered from these bands. Let's start from the band that was characterized by the translational behavior. This band is associated with a 3 meters deep channel. We can see velocity distribution at the ebb and flood stage. The maximum velocity was about 40 centimeters per second and was in the landward side, was measured in the landward side of the band during the ebb phase. Actually, the key points which are coming out from ADCP measurements are that the same area can experience opposite flows, but with very strong, with velocities that are quite different. This is quite expected in a meander band, because we know that tidal currents in band, they are described as mutually evasive, because the maximum velocity zone shift along the band during the ebb stage and change position during the flood stage. And this is quite clear here. For example, in this area of the band, the seaward side, we can clearly see that during the flood stage, we have a maximum of velocity, but in the ebb stage, velocity is, of course, water is flowing in the opposite direction, but with a very low velocity. This band is quite sharp, and this is characterized also by flow separation. And the flow separation process causes development of local recirculation. And this local recirculation prevents some areas from experiencing opposite flows. This is quite relevant in terms when we, for example, try to analyze paleocurrent distribution within this band. This band is quite interesting also because we can clearly see that in the downstream side, where we recovered several cores, I'm showing here in the red transect where we got the cores, and the red square shows that there is, on top of the bar, is accumulation of fine sand, which is almost the coarser deposits that was accumulated on the bar. And these coarser deposits was reasonably accumulated by the flood currents, which reach the maximum velocity in this area. So if we consider that the accumulation on this side of the bar is dominated by the flood current, this is quite interesting, because this band, in terms of morphodynamics, is clearly dominated by ebb currents, because the ebb currents are shaping the band, causing the seaward translation of the band. But actually, deposition is strongly controlled by flood currents. This is a kind of counterintuitive relationship between the ebb and flood currents. The case characterized by expansion is a quite small channel. Velocity is just up to 20 centimeters per second. Also here, mutually evasive currents are pretty well developed, and the same area can experience opposite currents with different velocities. In this band, which is quite wide, we don't observe any separation of the flow. It's a small band. The point bar is mainly made of fine grain deposits, very rich in mud, so we use a laser granulometer to infer the grain size. It is quite interesting to see that in the upper part of the bar, we have the coarser deposits, and this is a clear effect of the maximum velocity, which is located close to the bar on the two sides of the bar, both during the ebb and during the flood stages. So in a sense, even if the bar is very fine-grained, we can observe clear coarsening upper grain size strength. If we analyze the straightening to spade band, which is developed with bands which develop in a 3 meters deep channel, we see that here also velocity is not very high, just 20 centimeters per second. And here situation is quite variegated, because we can see that the same areas can experience opposite flows, and these opposite flows can show both similar and different velocities. Flow separation is just localized at few sites. And what is also interesting to note is that the deposits which are accumulated along the outer bank, which in a sense, they resemble the concave bench deposits described by Nansen, some rivers, Page and Nansen from Australia, they are characterized by a quite well-defined fining upper trend. which is consistent with the progressive shift in time that we observe from aerial photos, with the progressive straightening of the channel. Then the last case is associated with a cuspate band, stable cuspate. Here we didn't run any ADCP measurement, unluckily, because the channel was too shallow. What the main path of currents actually can be easily inferred from Google Earth images, and we can clearly see the path of the measured flood and ebb currents, and we can clearly see that they isolated deposits which we named as a barb, because they are detached from the inner bank from a barb channel that is cut in this side by the flood currents. Taking a core in the middle part of this barb, actually in the center of the channel, in the center of the barb, we noted, surprisingly, that actually the barb deposits are the only deposit that is accumulated within the channel, because just below the barb deposits, which are visible here in the core, we have salt marsh deposits with roots in situ. So shortly speaking, in this channel, we don't have any point bar. This is mainly an erosive feature with the just localized deposits represented by the barb. We used here some current meters to infer the velocity, and this band is characterized by velocity of about 40 centimeters per second, and the velocity are quite similar both during the ebb and the flood stages. So actually, we could make a summary of the features we actually describe, we infer from these channels, and you can see them. Actually, most of the planform behavior, they reflect what we observed from in fluvial systems, for example. Expansion is quite well common in rivers, and translation and ice stream migration as well. Straightening to spade planform behavior, as I just told you, can resemble some concave bench deposits, but for sure, stable to spade forms are typical of a tidal set. Actually, if we try to infer some key points from a description of these study cases, we can clearly note that, as I told you, this planform transformation resembles some fluvial meanders, but actually what we infer from grain size distribution is tightly related with tidal processes, like, for example, of coarsening upward trends in expansional bands, or coarsening upward trends also in translating bars. Actually, in this case, the signature of tidal processes is in terms of grain size is expressed by the grain size distribution along the bands. Actually, the asymmetric growth styles of some of the bars, I'm here referring to downstream migrating bars, reflects actually the role of tidal asymmetry in shaping meander bands. A warning now. Actually, we did these observations, but these observations are limited to a restricted number of study cases, and also ADCP measurements were limited in time, and also we analyzed small scale channels. So this is for us at least a starting point to develop this stopping at a deeper scale, and maybe to find other cases all around the world still developed in microtidal setting. The next issue will be about the lateral migration and vertical aggradation. Actually, this point arises it's been raised for small-scale channels ranging in depth from 1 to 3 meters, and is based on the idea that the vertical aggradation of overbanked areas, that ranges that can be quite high, more than 1 centimeter per year in the southern Venice Lagoon, could interact with the lateral migration of these channels to shape different geometries of point bars. Actually, to investigate this, this was the main topic of Marta Cosma's PhD project. Actually, Marta, to investigate the issue, she worked on the trajectory of point bar brink and channel talweg. So we need to define what the point bar brink is and what the trajectory of the point bar brink is. Actually, the point bar brink is the place of break between the bar top and the bar slope. The channel talweg is much better known, is actually the deepest part of the channel. When we consider these morphological elements in course, channel talweg can be easily detected where the channel lag deposits are found in course, and the bar brink can be placed actually where we see a change from bar top sub-horizontal lamination to bar slope inclined laminations. Actually, if we detect the bar brink and the channel talweg of a bar and at different times, that means scoring along the bar axis, along the direction of bar propagation or bar migration, we can actually define the brink and the talweg at different times and define the trajectory of the bar brink and the channel talweg. So actually, Marta studied different channels, recovering core from the axial part of the channel in different part of the lagoon, in the northern lagoon, where the aggradation rate of the marshes is slightly lower, and in the southern lagoon, where the aggradation rate is slightly higher. And these are the results. Actually, in green here, we have salt marsh deposits, and bar deposits are in yellow. This figure is much clearer. Actually, what we noted is that bar brink trajectories are always rising, and they strongly differ from classical models where we would expect a kind of sub-horizontal trajectory of the brink point. And there is a wider variability in terms of channel talweg trajectories. They commonly move down, they are descending at the early stage, and then they start to move parallel with the bar brink trajectory. So we can summarize the result of this work. Actually, bar brink are always ascending. They always define ascending trajectories, and they never descend. This is simply due to lateral migration of a bar under aggradational conditions. Actually, the trajectories we identified are not always linear. Linear trajectories simply document a stable ratio between lateral and shift of the channel and vertical aggradation of the marsh. In some cases, we also have nonlinear trajectories, which can be ascending concave upward or ascending convex upward. And these cases simply represent a change in the ratio between vertical aggradation of the marsh and the lateral shift of the channel. In channel talwegs, we have both descending and ascending trajectories. Descending trajectories commonly characterized, as we see here, the early stage of channel development. Simply the channel goes into its formative shape, and then trajectories are ascending, documenting aggradation of the channel floor. Actually, if we consider the relationship between brink and talweg trajectories, we clearly see that we have three main situations. Trajectories that can diverge. This is typical of the early stage of channel development. The channel goes into its own formative discharge. Then we have also parallel trajectories. I'm pointing here to an example from the southern Venice Lagoon. After the early stage of channel formation and downward shift of the talweg, we have the talweg trajectory that runs parallel with the brink trajectory. This means that the channel reaches its own formative discharge. It was keeping its shape as a stable. And in some cases, of course, we can also see, this is the case, the dramatic rise of the trajectory, which is not pointed out here, that is associated with the rapid infill of the channel. So actually, the aggradation of the overbank areas of the marshes can play a key role in shaping tidal point bar deposits, especially in small-scale channels. And actually, there are evidence in literature of this process also for larger channels. We have here some examples from the Netherlands, from seismic data, which are showing the progressive deepening of a channel, so a downward shift of the channel Thalweg that is associated with an increase in tidal prism. But what is surprising is that also in fluvial deposits, we can see a gradation of the Thalweg and the green of the green point, especially in systems which are characterized by very stable channels in highly vegetated and highly aggrading floodplains, like the deposits, neogenealogical deposits from the Czech Republic, described by Lichny in 2005. Actually, to better understand this process, we also collaborated with Nigel Moulton, Luca Colombera, and Ayan from University of Leeds to develop some 3D forward models, stratigraphic models using PB sand. Actually, in this model, Marta used the same field data I just showed you as input for the model, providing channel dimension, style of transformations inferred from historical aerial photos, aggradation rate, and distribution of sedimentary facies. Actually, we use, as I just told you, field data to define the morphology of the surface that is generated in a 3D space by the progressive shift, lateral and vertical shift of the bar brink. Here I'm just showing some results from the bar brink of one of the study bar. And actually, Marta played different types of planform transformation. Actually, we know that the specific band like this was just expanded. I'm just showing one case. And she just played with, for example, a pure expansion, or she combined expansion with other types of planform transformation, like interaction between expansion and rotation. In this case, actually, they realized that different planform transformation, they can play a key role in shaping the surface generated by the lateral and vertical shift of the bar brink. So also planform transformation should be considered in analyzing different shapes of trajectories generated by these bars. The next issue I would like to discuss is about bar deposits and the possible tidal signature in these deposits. I will start from channel lag deposits, which are, as we would expect, quite rich in shell and shell debris, as commonly described by many tidal channels. There are, of course, mudclasts, which are commonly spherical and always quite large in size, almost pebble-sized mudclasts. The coarsest lag we have seen, we will see in the next slide, is made of medium sand. So actually, these are quite fine-grained lag deposits, and here you have a couple of examples of the grain size of the sand that commonly occurs in lag deposits. To interpret this, to make some consideration about these lag deposits, we also should consider the role of a microtidal range in formation, for example, of mudclasts. This is quite an interesting issue because if we consider the tidal range in Venice, this tidal range can manage to expose the whole point bar only for very, very small channels. Actually, here you have a photo of a 3 meters deep channel at the low tide. Actually, only the uppermost part of the bar is exposed. This is nothing comparable with what happened in a hypertidal range, like in Mont Saint-Michel, where at the low tide, also the channel is exposed. As a consequence, we don't have mud cracking of point mud deposits. We don't have production of flakes of mud for this cracking. And also collapses of the bar is prevented. So shortly speaking, most of the mudclasts which are recovered from the channel lag deposits are just coming from outer bank collapses. Here is a nice photo from a present-day channel with some marsh, salt marsh vegetation that is still attached to the block. This explains, following also some observation by Liotta from a recent paper, the shape and the size of this class. They just come from big blocks collapsing from the outer bank. And we don't have any cumulative class that is actually generated by cracking of the bar. Point bar deposits, as I just told you, these are quite fine-grained. You see, this is a large channel, 7 meters deep. Here you have some results of grain size analysis. They also include the lag deposits, but more or less the grains, most of the bars are just made of fine sand to very fine sand. If we have a look at the deposits, we clearly see that they are very well laminated. In some cases, if you are lucky, here we have both vibra cores and auger cores. Lamina are very well visible, and they commonly dip toward the channel between 10 and 25 degrees. So if to try to summarize the main sedimentological features of the deposits, we could say that they are very well laminated. They are quite rich in plant debris. The key point is that they don't show any cross strata or cross lamination. There are just minor subtle changes in deep angle of lamina. And if we are interested in looking at the classical rhythmites or the cyclic organization of changes in lamina thickness, they are locally developed, but just at the millimetric scale. Look at the scale here. We have a progressive decrease in silty laminae and sand laminae, but these are just 2 millimeters. So at the beginning, we were quite surprised about missing cross laminations. So maybe the problem was in the technique we used for coring these deposits. We also did some try, but actually we did that coring with the same technique using auger cores in the Mont Saint-Michel Bay, coring point bar deposits here. We recovered very nicely developed rhythmites and also cross strata. So it's arising that actually this point bar deposits, they don't have any clear cyclic or rhythmic organization, which is considered the most classical tidal signature. And also they don't show development of clear bed forms, ripples, for example. This could be actually due to the limited amount of deposits, sandy deposits, which are available as bedload in the system. Because actually, as demonstrated by several numerical models and field measurements, most of the sediments within these channels simply move as a suspended load. Actually, the only clear evidence of tidal processes which we detected from the point bar deposits are just double mud drapes, which are clearly documenting a minimum removal of sand. Again, look at the scale. This is just 1 millimeter thick lamina with muddy lamina associated with the slack water stage and less than 1 millimeter of sand that is transported during the ebb or flood stage. The bar top deposits are commonly, obviously, muddy, colonized by vegetation. So we have root traces and they are commonly oxidized. Interesting point is that locally, and locally means where the channels are very close to tidal flats, these bar top deposits, they host sharp-based sandy laminae, which are commonly consist of very fine sand, pretty well sorted. And these laminae are interpreted as the record of storm events, which we know with the bar top during the Bora wind storms. So to summarize, to sum up, these are the key sedimentary features of this microtidal point bars. In the bar top deposits, actually, we can observe just a gradation of muddy marshes, and the only record could be actually seasonal in a sense, because the only record we can get from these deposits is related with storm events. The bar bodies are pretty well laminated, and the only evidence of a tidal signature is represented by mud drapes. We don't have any evidence of subaerial exposure, and we don't find any cross strata or cross lamination. Rhythmic deposition is almost not recorded, and possibly developed at millimetric scale. Channel lag deposits are very rich in shells, and the mud casts are commonly provided just from collapses of outer bank deposits. The last point I would like to touch is getting late. I apologize for this. Is just about subtidal meanders, which are quite common in the Venice Lagoon. Actually, subtidal meandering channels are the only other example we know of subaqueous channels. We know a lot about turbidity currents and related channels, but we don't know too much about subtidal channels. There are examples in the southern Venice Lagoon. They are still active. Other channels are buried in the northern Venice Lagoon, as we can see here from this photo, very close to Venice, a nice meander here developed in a subtidal set. This study is part of the PhD of Elena Bellizia, PhD project by Elena, and Elena studied a meander in the northern part of the Venice Lagoon. Actually, this is a buried meander. The presence of this channel has been highlighted by, of course, geophysical data, seismic data, and in the frame of a previous project, the EOS project, and the general pathway of this channel has been highlighted in previous publications by Ricardo and Donici. And actually, the origin of this channel was tied to a subtidal environment, also by previous studies, simply because core recovered across the point bar deposits don't show any evidence of oxidation on top of the bar, no roots, and also the foraminiferal assemblage that was recovered by the bar top deposits is not consistent with a marsh with a, let's say, subaerial setting. So this channel was interpreted as a subtidal channel. Actually, this is a quite nice image. The quality of data is locally not excellent, but the strength of this study is the huge amount of seismic section that was elaborated by Elena. She managed to do a 3D reconstruction of the channel. The channel defines in this area 3 main bands, and it's quite nice to see that within the main point bar that is fully visible here, there's a huge amount of overband deposits preserved. This points out that this channel started to create the point bar from an already sinuous trajectory. So it was not straight at the beginning of its own life. But even more interesting is that considering different backsets, which are visible in different seismic sections, Elena was able to detect different scroll sets that are just different stages of growth of different bars. Similar approach we used recently by Podgurkin, reconstructing the planform evolution of fluvial point bars in dinosaur formation. Actually, this process allowed to reconstruct the planform evolution of the bar, showing that also subtidal bars, subtidal meanders, can migrate and evolve with following different planform styles, planform growth styles. So we distinguished several stages of bar growth, which actually document a dominant landward or seaward accumulation of the bar. So actually, this demonstrates that subtidal point bars are actually quite dynamic features, and they can be affected by different styles of planform transformations. Actually, when we try to understand the processes occurring in subtidal point bars, we shifted to the south, and we decided to analyze a point bar that is still growing close to the Malamocco inlet. And at this side, we also ran some sub-bottom profiles. So we got a lot of seismic sections. We recovered some sedimentary cores. Unluckily, the signal is not perfect. There's a lot of gas in these deposits, but the quality of the section is enough to allow us to detect subhorizontal bar top deposits, clinoforms, and we can almost see the base of the bar here. There's an interpretation which is also highlighting, this is a quite interesting point, the presence of internal truncations like this one, internal conformities within the clinoforms. So I'm just now highlighting sedimentary features of bar top deposits and the deposits which are associated with these truncations. In this case, if we look at the bar top deposits, we can clearly see that these deposits are sharp-based. There is an unconformity between the clinoforms and these bar top deposits. They are slightly coarser than the deposits which are underlying the unconformity. They include some mud layers, but they are mainly horizontally bedded, and they include some sandy, sharp-based sandy layers with a considerable amount of shells, which are commonly fragmented and abraded. Obviously, this let's call bar top unconformity is visible also in other parts of the bar, not only along the apex where this cross-section has been reconstructed. If we move down just below the horizontal bar top deposits, and we try to have a look at the deposits which are accumulated in the nearby one of these unconformity, we can see that there are some intraclass at the depth where we estimated the presence of the unconformity. Actually, just above the unconformity, we also observe the presence of inverse graded layers. As for the rest, actually, the sedimentary features of the cryostratified deposits are pretty similar to those we have seen from point bars developed in a saltmarsh setting, in channels draining saltmarshes. So actually, what is the origin of this sharp base for the bar top beds and these scours here? What is the origin? Actually, we interpret these deposits as the effect of storm conditions. So I'm, in a sense, now stepping back to the interaction between storm events, wave-related currents, and tide currents. Actually, what happened in this model? During fair weather conditions, okay, in a sense, we would say with no bora wind in the southern Venice Lagoon, tides are the dominant current. So in a sense, here we have a tidal dominated sedimentation. So redistribution of sediment within the bar is just controlled by tidal currents. But during storm conditions, actually related with the bora wind and intralagoonal waves, actually we can have a quite strong wave bar top winnowing. In a sense, the bar top area here from the hydrodynamic point of view is a kind of offshore transition zone. Mud during fair weather stage and the sediment remobilization and formation of, we could call this sharp-based sandy layer tempestides, in a sense, during storm events. These storm events are also thought to trigger collapses of the bar rim zone. And these collapses actually generated the truncations, which are highlighted by the seismic profiles. And these depressions are commonly filled by deposits which are provided by the bar top zone, as attested by developed of inversely graded layers, which are probably small debris fall deposits associated with avalanching processes generated to fill these collapse scours. And that's all, in a sense. Actually, I could summarize the key point we discussed because I'm almost running out of time. Again, apologize for this. Microtidal meanders of the Venice Lagoon show planform morphology that is actually comparable with the bands that are formed in settings with a higher tidal range. And their migration rate, they are not lazy meanders. Their migration rate is not so dissimilar also from fluvial meanders, if properly normalized with a local channel width. It's quite interesting to note that the microtidal meanders are characterized by a quite variety of planform transformations. These styles of transformation partially overlap those of fluvial channels, but mutually evasive currents and tidal asymmetry can actually imprint a tidal signature on the architecture and grain size distribution of point bars. So in this case, this is quite interesting to know that the tidal signature is expressed in terms of morphodynamic evolution and in terms of architectural deposits and grain size distribution. Accordingly, in this setting, the tidal signature is not expressed in terms of sedimentary structures. Point bars in this setting, especially those formed by small channels, can be shaped. The geometry can be shaped by the interaction between the rate of lateral shift of the channel and the vertical gradation of surrounding marshes. And actually, when we go and look at the sedimentary structures within this point bar, as I just told you, they don't have classical diagnostic sedimentary structures, and the only exception is represented by the occurrence of double mud drapes. And finally, we defined also the first description about subtidal point bars, which can evolve under different styles of planform transformations, and they can be affected by they can be strongly shaped by the interaction between tidal flows and intralagoonal waves. And at the present, the main question is, what about these features? Are they spread also in other sites? And would be really curious to see if these similar sedimentary features can be observed in other sites characterized by a microtidal setting. But this is a matter for coming studies. We'll see. And thank you for your attention. Apologize for 45, maybe more. Sorry.
It's absolutely fine. Thank you so much for a wonderful presentation, Gino. It's an absolutely amazing amount of data, how much they have in that presentation. So that's fantastic to see. So the question, the chat is now open for questions. Whilst you're typing them, please go ahead and make sure that you send them to everyone, because if they go to Seds Online, we can't see them. So please do that. And also tell us where you're messaging in from as well, because it's always good to see the reach of Seds Online around the world. I can also tell you that the forums are back online. It's only taken a little while, but hopefully you can see that we have given the website a little bit of a facelift, and we're really happy with our new format and how it all looks now. So it was worth the wait, I hope. Yeah, so go ahead on the forum. So if you're watching this on the recording, please go ahead and ask questions on the forums too, and we can keep this conversation going. So yeah, any questions that you have, please stick them into the chat, message them to everyone. We have a first question from Claire McGee, who says, thank you for the talk, Gino. What impact has the Holocene transgression had on the composition of the point bar sediment during sea level rise and subsequent high stand? Do the point bars still prograde during transgression when the valley is being filled? Is this what promotes the vertical aggradation within the channels?
Good point, of course, is the transgression, which is actually promoting it's actually the present day sea level rise joined with local subsidence, which is actually promoting the vertical aggradation within the channels. And actually, marshes they manage to keep pace with this progressive sea level rise. Let's call it base level, because actually is an effective combination between sea level rise and local subsidence. It ranges from the northern to the southern side, to the southern part of the lagoon, and this is actually the key forcing on the aggradation of the channel. And thinking about the issue about the composition of the point bar sediment, actually we have data just for the present day bars. So actually that would be difficult to see if old tidal bars have sand that is sourced from different systems. In a sense, the present, most of the sand is a kind of recycling of previously accumulated deposits. So we would need some more data from old point bars, which are buried under the present the surface of the marshes. So not sure about the composition.
Okay, great. Our next question is from Valentin Zucat, who says, "Hi, Gino, absolutely amazing work. And this data set, I know, I said it too. Anyway, fast forward a few million years when geologists can do field work again. How easy do you think will it be for geologists to recognize that this system was mostly dominated by tidal processes?"
I love this question. Thank you, Valentin. Actually, that would be quite difficult because actually I tried to point out this during the presentation. We are used to think that we see tidal diagnostic sedimentary structures. We see a lot of them, so the system is tidal dominated. Actually, this is not true at all. We can have plenty of tidal signature in systems which are fluvial dominated. This has been widely demonstrated by several studies. So actually, tidal dominance is tightly related to a dominance of tidal currents on morphodynamic processes. So from this point of view, I think it's much more relevant to analyze morphodynamic evolution of bars instead of looking at sedimentary structures. In a sense, here we are lucky because we don't have any sedimentary structure to observe. And if we analyze these deposits in the rock record after a million years, actually we would not detect them as tidal in terms of presence of sedimentary structures. But if we manage to identify the planform evolution of some bars, or let's call the anomalous vertical grain size distribution within these point bars, that would be a kind of a smoking gun to detect their tidal origin. That's the point. Hope you answer the question.
Great. No, that does answer the question. I think that's great. Thank you. Next question is from Howard Fellman, who says, "I have looked at sinuous tidal channels in muddy flats in Arcanon in France and Willapa Bay in the USA, and they are stable for decades. So why do some channels meander and others don't?"
That's a very good point. And actually, the size is obviously a key point. And as a second point, I would list the grain size of outer bank deposits. Because, for example, we know that what we look from above as a muddy tidal flat below could be quite heterogeneous. For example, they could have some buried point bars, which are slightly sandier than the rest. So actually, if we see channels with the same shape and the same size, one can be more stable simply because the outer bank is very muddy, and the other one could be much faster because the outer bank is cut in sandier, less cohesive deposits. So this could be a feature that could control a different lateral migration rate for channels which are just showing the same size.
Okay. Our next question is from Cynthia Hagstrom in Calgary, Canada. She says, "Ciao, Gino. Thanks for the talk. Do you think the subtidal meanders will aggrade and eventually become subaerially exposed?"
That's a very good question. Unluckily, in the Venice Lagoon now, tidal flats are becoming deeper and deeper. The sediment budget is negative because actually what happens is that during major storms, mud is suspended from the tidal flats, and then it moves away from the lagoon through the inlets during the ebb stages. So actually the tidal flats are the subtidal platform are actually getting deeper and deeper. Obviously, if we manage to inject some sediment, for example, if we would have another different rivers, not spring rivers in the Venice Lagoon, if we would have a river that provides sediment to the lagoon, of course, we could get a process like this. Tidal flats could turn into marshes, and subtidal channels, they could become marsh meanders draining some marsh setting. shortly speaking, I don't expect that the submerged meanders will emerge soon in the Venice Lagoon. But this process is possible, of course.
Okay, cool. Our next question is from Susan Dietz, saying, thank you for the fantastic talk. Have you had a look at the ethnology of these microtidal channels, and how does it compare to other tidal settings?
Yeah, this is something that is actually missing. I have to write hands up about this. I apologize, but actually we still have to do something about this, and that would be very interesting. That would be very interesting because maybe that ethnology could provide crucial information about deposits accumulating different tidal range, and this would be a really important issue to investigate, because that could provide insights to at least to speculate about tidal range in the rock record, and that's a really crucial point. But by the way, I apologize. We don't have data about technology in our deposits. I apologize for this. It's a great lack.
Well, possible future project then. You've got plenty of other data. It's great. Next question is from Patrick Hansel. It says, thank you very much for the informative talk. Are the sedimentation conditions in the Venice Lagoon comparable to those in the Wadden Sea? And he's from Bavaria.
It depends what you mean by sedimentation conditions, because actually, yeah, this is quite, there are quite wide spectrum of features we should consider to run this comparison. Tidal range is, of course, different. And then the Wadden Sea, as far as I know, waves that they can have a role in controlling, or at least interacting with the tidal processes. And as far as I remember, the amount of suspended sediment is slightly higher. I remember fluid mud condition in the Wadden Sea, if I'm not wrong. And so maybe some features could be comparable, but there are for sure also some differences. Again, it depends what you mean by sedimentation conditions. It's a big pen to include a lot of features. So I'm not sure I got your point.
Patrick, if you'd like any further confirmation, please ask another question, then I think we'll save. So from next question is from Kazuma Toda, who says, thank you for a great talk. Can you give some ideas regarding the relationship with water discharge compared with the fluvial channel? So can the water discharge control the tidal and fluvial channel morphology?
Yeah, that's a great point. Actually, I would face this point from the, let's say, philosophical point of view now. I just discussed concept because we don't have quantitative data to discuss this. A key point is actually that if we want to make a comparison between tidal channels and fluvial channels, we tried, Alvise Finotello discussed and highlighted this point in a couple of papers. The key point is that, for example, we know that the formative discharge, the best discharge for a river, is the bankful discharge. Okay, we know that at the bankful, meandering rivers are working very well, and point parts they grow. Actually, if we consider tidal channels, at least those of the Venice Lagoon, but I think we can apply this concept also to other tidal ranges. Actually, at the bankful stage, we have a slack water stage, and the maximum efficiency in terms of flow is halfway between the slack water stage and flood stage and upstage. So this is a remarkable difference between tidal and fluvial channels. So for sure, this should be considered when we go to analyze the evolution, planform evolution of these channels and morphology of these channels. This is one feature. And of course, the key role of tidal currents in terms of morphology is is mostly expressed when we consider the cuspate bands, which are typical of tidal environments. We don't know any cuspate band from a fluvial realm. And in this case, the key point is not in terms of discharge, but is again in terms of mutually evasive currents, which are shifted on the two sides of the band during flood and ebb tide. So discharge should be considered for the previous point, bankful conditions or not. And in terms of morphology, I would prefer to consider mutually evasive currents instead of the amount of water discharge.
Okay, fantastic. So if anyone has any further questions, you could, oh, we have one more. A question from Jason Pincer, who asks, is it possible to form oxbow lakes like those in the fluvial environment?
I would like to have Alvise Finotello on my side. He's crazy for this topic. Of course, we have plenty of oxbow lakes in the Venice Lagoon, and there are, but not only in the Venice Lagoon, all around the world. There are a lot. I showed one in the presentation. If you go to the record of you can find there's plenty of these abandoned channels. Actually, I think this is a relevant topic in terms of development of oxbow lakes. Actually, we have oxbow lakes, and they are always associated with neck cutoff processes. We never documented any chute cutoff process. And this is reasonable to us, simply because cutoff processes are associated with a considerable amount of water which is overpassing the bar. You need to move water over the bar to develop the chute channel and to cut off the band. And in tidal setting, these, at least in tidal channels which are draining in marshes, this is quite difficult to do, because when you have high water, water is just standing, so you don't have any flow which is overpassing the bar. So actually we could assume that in these systems we can only get neck cutoff, and we cannot get chute cutoff.
It's a fascinating contrast. It's really amazing.
Yeah, it's nice.
Thank you so much for presenting, Gino, and thanks everyone so much for your questions. A really great range there, I think. And we had questions there from Calgary to Erlangen as well, which was great. So we hope to see you next week at the webinar, A Guide to Earth, Life and Terrestrial Carbonates for the Intergalactic Sedimentologists. So it's very, very broad, that's fantastic. So I hope to see you at that. And that will be presented by Alex Brazio of the University of Aberdeen. In the meantime, please come along to our Seds Online coffee breaks, go and have a look around our new look on the website. We're still working on parts of the website, so do bear with while we get that completed. But yeah, and I'll see you in forums perhaps. So see you next week, if not before then. Thank you.